Okay, Bismillahirrahmanirrahim. This lecture, online lecture, we are going to do. I'm going to give this online lecture because of the current situation of the country. So the subject is finite element analysis, right? जैसे मैंने आपको पहले बताया था कि in finite element analysis, what we do is we take, for example, we have a simple problem. यहाँ पे हमारे पास एक simple problem statics के लिए लेते हैं. For example, we have a simple problem. We have a I section like this. And we have a force of 1800 Newton applied on this end, and we have a fixed end over this side, right? Let's make it a little symmetrical. Okay, let it be 2.5 centimeter. This length is 10 centimeter, and this length is 2.5 centimeter again, right? And the width here is 2 centimeter, and the total width is 8 centimeter, right? Let it draw here. Let it be. So it's 8 centimeter. So in finite element analysis, what we do, we divide the problem into finite number of elements. For example, we have this problem. So what we will do, we will divide this problem into 3 elements. For example, this one rectangle, second rectangle, and we have the third rectangle over here. So here we have 3 elements, element number 1, element number 2, and element number 3. Because we are doing one-dimensional problem, right? So the nodes will be one-dimensional. What does that mean? For example, we have node number 1, node number 2, node number 3, and node number 4, right? So we can draw these nodes like this. For example, we have a node here. We can have a spring-like thing in between them. Right? So you have to node 1 आ गई, node 2 आ गई, node 3 आ गई, and we have node 4. In one-dimensional problem, we assume that we have a deformation only in one direction. In one-dimensional problem, there is a deformation only in one direction. Let it be y direction only. Right? Actually, it doesn't happen like this. Actually, so my pass, if you apply a force in one direction, we have deformation in all 3 directions. But we assume in one-dimensional problem that we have deformation only in one direction. So from in this problem, we will take the elements one by one. For example, we have taken element number 1. So it's element number 1. So is the element number 1? We'll solve the elements one by one. So this is element number 1. In element number 1, we have node number 1 and node number 2. And the element is 1. So what we have is, we can have the equations for the nodes. Let it be node 1, right? In element number 1, we have the node 1. In node 1, we have this force, upward force R1, which is a reaction force, and the downward force F1, right? So what is that F1? When the last lecture I told you, when we are doing structure problem, we have F over A equals to E A delta L over L. From where it came? It come from is equal to E from the Hooke's law, right? So F will be equal to, sorry, A will go there, right? So it will be if E A over L, we take it as a constant, then that will be K. So we take K is equal to E A over L. So F will become K delta L, where F is the force, delta L is the deformation, right? So this is the force. So we have this problem. We can write it F is equal to K delta U as well. And in the book, the notation delta U is used, right? So F is equal to K delta U. Delta U is the change in the deformation, right? Change in the deformation. For example, for node 1, we can have this F1. F1 will be equal to K1, which is the stiffness constant for element number 1 into U2 minus U1, right? K1 into U2 minus U1. So this force is like R1 or F1 is equal to K1 U2 minus U1. So we have an equation for the element node number 1. Equation for node 1 is R1 minus F1, which is equal to 0. So that will be R1 minus K1 into U2 minus U1 is equal to 0. So that will be equal to K1 U1 minus K1 U2 is equal to minus R1, right? Similarly for node number 2, for node 2, we have the equation, here we have the node number 2, and node number 2 we have two forces. This element 1 is applying a force upward, this element 2 is applying upwards on this node downwards. So on node 2 we have this force which is F1, and we have this force downwards which is applied by the element number 2, that is F2, right? So F1 will be equal to K1 U2 minus U1, right? And F2 is equal to K2. K2 is the stiffness constant for element number 2, U3 minus U2. So if we sum these two equations, that will be F1 minus F2 equals to 0, and that will be equal to K1 U2 minus U1 minus K2 U3 minus U2 is equal to 0. So that will be equal to minus K1 U1 plus K1 U2 minus plus K2 U2 minus K2 U3, right? Okay, let me write this equation as equation number 1, and this equal to this equation as equation number 2. Okay, then we have equation number, and then we have the node number 3. For here we have node number 3. On node number 3, element 3 will be applying a force upward, element 2 will be applying a force upward, that will be F2, and element number 3 will be applying a force downward, that will be F3. So if I draw this force over here, so here we have F2 on element and on node number 3, and we have a force downward by element number 3, right? So how can I write it? That will be F2 equation for node 3. So that will be F2 F2 minus F3, upward force minus downward force will be equal to 0. So that will be K2 into U3 minus U2 minus K3. Now K3 is the stiffness constant for element number 3. That will be equal to U4 minus U3, and I'll put it equal to 0 because that's in equilibrium, right? So we will simplify this. So that will be equal to minus K2 U2 plus K2 U3 plus K3 U3 minus K3U4 is equal to 0. You can take U3 common from here, so that will be minus K2U2 plus it's K2 plus K3U3 minus K3U4 is equal to 0. Now we have the last node. This is the last node. On this last node, element 3 apply the force upward, and we have a downwards action force of 1800 Newton, right? So on node 4, what is happening? We have this upward force that is applied by the element number 3. We have this downward force which is 1800 Newton, or we can simply write it P. So that will be equal to F3 minus P is equal to 0, right? So that will be F3 will be K3 U4 minus U3, that is delta U, K delta U, right? Minus, take it to the other side, is equal to P, right? So this will be equal to minus K3U3 plus K3U4, right? I told you the steps of in the first lecture. I told you that we have a pre-processing phase. In pre-processing phase, we have few steps. Well, the steps are to discretize, that is divide the problem into a number of elements, right? That was discretization that we have done. Second step was to write mathematical equations for each node or element. For each node, in this problem we are going with nodes, right? The equations for each node, right? Then now the third step is to assemble all the nodes, all the equations, right? For all the nodes, assemble all the equations. So how we will assemble? We will write the equations, all equations. So here we have the equation number 1, equation number 2, here we have the equation number 3, and equation number 4. We will write them with K1 U1. This is equation number 1. I'm writing K1 U2 is equal to minus R1. Then we have, okay, B towards the first level, minus R is equal to minus R1. Let me write it on the new page so you can get. So it's K1 U1 minus K1 U2 is equal to minus R1. Then we have this second equation, which is, here we have, and this we can take a common U2 common, we'll take common, right? So that will be minus K1 U1 plus K1 plus K2 U2 minus K2 U3 is equal to 0. Then we have the third equation. Here we have the third equation, that will be U2 or U2 के नीचे लिखेंगे, that will be minus K2 U2, right, plus K2 plus K3 U3 minus K3 U4 is equal to 0. Then we have this fourth equation, which is minus K3 U3 plus K3 U4 is equal to P. Now we can write these equation in matrix form. So it's simple. It's K1 minus K1 0 and 0, right? Minus K1 plus K2 minus K2 and 0. We have 0 minus K2 plus K3. These K2 and K3s are the stiffness constants for each elements, right? Because we have 3 elements, so we have the stiffness for 3 elements, K1, K2 and K3. So we will multiply it with the deformation U1, U2, U3 and U4, and we will put it equal to the force matrix. So that will be minus R1, 0, 0 and P. So here we have the force matrix. This is the stiffness matrix. This is the deformation matrix. Right? So this will be K X K or K delta U. Maybe you can write K delta U is equal to F. So there is the matrix. We have written it in the matrix form. So now the next step, as I told you, was to, and in this I told you that the fourth step is to apply boundary conditions. Now in this problem, what are the boundary conditions? Boundary conditions are, we have 2 boundary conditions. The first boundary condition is that U1 is equal to 0. What does that mean? It means that on this node U1, on this node we will have U1, that is the deformation in node 1. This is U1. In this node we will have U2. In this node we will have U3. In this node we will have U4, right? So in this node, because it's fixed, so that is why U1 will be equal to 0. This is the first boundary condition. And on this we have, that is a 4, or we call it P is equal to 1800 Newton. So these are the 2 boundary conditions we are going to apply. So how are we going to apply the boundary condition? It's a simple method. We will write this equation in the first line, right? Okay. Now how can we apply this boundary condition? So here we have U1, right, is equal to this matrix. So we will keep it 1, 0, 0, 0 equals to 0. Now this equation is showing that U2, U3 and U4. Now this equation, if we multiply this equation, U1 will be multiplied with U1, so that will be U1. All other zeros will be multiplied with U2, U3 and U4. So we can read this equation like U1 equals to 0. We can apply a boundary condition like this. So we apply a boundary condition in a reverse direction. U1 we will put it equal to 1. In this place we have put it 1 and all zeros, then this will be equal to U1 equals to 0. Baki sari equation we will write it like that. Minus K1 plus K2 minus K2 and 0, 0 minus K2 plus K3 minus K3, 0, 0 minus K3 and K3, and here we have 0, 0 and 1800. Now if you can see this whole column is being multiplied with the U1, which is 0. U1 we know is 0. Now this whole column is multiplied with this 0, right? So all this column, in the next step we can make all the column equal to 0, right? So it's 1 over, you can write it 1. So K1 plus K2 minus K2, 0 minus K2 plus K3 minus K3, 0 minus K3 and K3. So It is u1, u2, u3, u4 is equal to 0, 0, 0 and 1800. So we can cancel out this whole row and this whole column. It will be a 3 by 3 matrix now, which we can solve it easily on the calculator. So it will be a 3 by 3 matrix like k1 plus k2 minus k2 and 0 minus k2, k2 plus k3 minus k3 minus k3 and k3. There we have 0. It's u2, u3 and u4. We put it equal to 0, 0 and 1800. So this is how we apply the boundary conditions. And the next step was to the solution phase. After pre-processing phase, there comes the solution phase, right? So here we have the solution phase. After this pre-processing phase comes the solution phase. In solution phase, we are going to solve this matrix, but before solving it, we know that K was equal to EA over L, right? So we will solve it for elements because we have the stiffness for the element. For example, we have this element number 1, which has a length of 2.5, right? And we can find the cross-sectional area because we have this width that was 8 centimeters and we have the thickness given in the book, right? We will apply a value of thickness. We have the value of E. We can find A. We have the L. So from where we can find K1. So let me give you the value of E and the thickness. So the thickness given in the question is 6 millimeter, and these are centimeters, right? And we have the value of E, which is 68.9 into 10 raised to power 9 Pascal. We know that Pascal is Newton per meter square, so we have to convert all the other values of length into meters, right? So from here we can calculate K1. That will be 68.9 into 10 raised to power 9 Newton per meter square. And the area, we have the area for the element number 1, that will be 8, that will be 0.08 multiplied by the thickness 0.006, that will be the area in meters square, right? Divided by the length, that is 0.025 meters, right? So we'll get the answer in Newton per meter. This will be cancelled out with this, get the answer in Newton per meter. Okay, this will K1 will be so we have this value of 68.9 into 10 raised to power 9 multiplied by 0.08 multiplied by 0.006 divided by 0.025. So that will be 1.38 into 10 raised to power 9. So that will be the value of K1, 1.3228 into 10 raised to power 9. Similarly, we will have a value of K2 and K3 from element number 2 and element number 3. We'll put these values in this equation and solve it. You can solve it with calculators, right? So we will get the values of U1, that is 0, U2, that will be 1.36 into 10 raised to power minus 6 meter. And we will get the value of U3, that will be 2.31 into 10 raised to power minus 5 meter. And we will get the value of U4, that will be 2.45 into 10 raised to power minus 5 meters. So we will have this. right? We have these four values. So once you have got these values of deformation, becomes the post processing phase, right? Comes the post-processing phase. In post-processing phase, what we do, we calculate the other things like deformation, like stress and strain, and principal stresses, formative stresses, and other types of things. For example, if we want to calculate the stress from here, what we will do is we will just have E delta U over L. That will give us the stress. We have for element number, for example, for element number 1, we have the two nodes, that is U2 and we have U1. So for element number 2, we will have element number 1, we will have U2 minus U1 E. We have the value of E, we have the value of U2, we have the value of U1, and we have the value of L. We'll put it in this equation and we'll get the stress, that is 3.75 megapascal. Similarly, we will get the value of sigma 2, that is stress in element number 2, that is 15 megapascal, and the stress in element number 3, that is also 3.75 megapascal. So that was the end of the problem. So what we did in this problem is we took a problem and then divided that problem into finite number of elements. For example, in this problem we divided it into 3 elements and 4 nodes, and we assume that these nodes will only deform in one direction. They will stretch in one direction. Here we have the force, that force will apply on it and it will stretch only in the y direction, right? Then we take it node wise. For example, this was node number 1, right? On node number 1 we have the two forces R1 and F1, so we can write those forces like R1 minus F1 is equal to 0. And similarly on node number 2 we have two forces, that is F1 by the element number 1. Element number 1 is pushing it upwards, and the element number 2 is pushing it downward. So node 2 will have two forces on it. So we write it like this. This K is the stiffness matrix it comes from. I have shown you here. Here we have the K, which is the stiffness of the element. That is the end of the lecture. Thank you for watching.